Hello, this is Dr. Baxley. This is part 2 of the Chapter 7 lecture video about electrons and waves. In this video, we're going to start with a brief review of part 1 and then talk about waves and energy. I hope you have your lecture notes printed out. There are a few diagrams and problems to work on towards the end of the video. In the early 19th century, physicists and chemists were looking at properties of waves and particles. Remember from the previous video that waves can propagate from a source, and if they move through a slit, the waves will then diffract or spread out from the opening of that light source. You can see this in a room if you have a flashlight or a light source and it shines through an open crack in a door. Some of the light waves will spread out and illuminate more parts of the room than just in a narrow line. In terms of particles that move away from a source through a slit will not diffract. They'll just continue traveling in that straight path. This can be evidenced in a double slit experiment where a light source can be shined through an area with two slits. In that case, as the light waves diffract through the slit, they'll form interference patterns, both constructive and destructive, as the waves diffract through that slit. You can see this on a film, and this video helps animate what's going on, where the waves of light are moving through a two-slit experiment, and you can see dark spots and light spots as the waves start constructively and destructively interfering with each other. A few famous scientists looked at something called the photoelectric effect in the early 1900s. In this effect, some visible light is shined on a surface, and special metal surfaces with certain frequencies of light will emit electrons from those surfaces. This particular experiment shown on the right side of the diagram exemplifies how this would work. A light source is shined onto the metal surface. Electrons can be ejected, and those electrons can then follow through an electrical circuit and register a current if they're moving. Here's a graph of the data from that kind of an experiment. On the y-axis, there's the rate of electron ejection, and on the x-axis, there's frequency of light. As we look at their experiment, there are no electrons being ejected from the surface at low frequencies of light. It's only when a certain threshold frequency or minimum frequency of light is shined on the surface that electrons begin to be ejected. At low intensity light, there's a smaller number of electrons ejected over time, and at higher intensity light, more electrons get ejected. This showed that light can act more like a particle than a wave, because if light truly acted like a wave, the energy of those light waves could build up over time, and regardless of their frequency, they would eventually have enough energy to push electrons away from the surface. But this isn't the case in this experiment. There's a threshold frequency, or minimum energy, because recall that energy is related to a constant times the frequency. It's only until a certain energy has been reached that electrons can be ejected. One of the scientists that was investigating light and energy was Max Planck. He was a German chemist and physicist that worked around the early 1900s. Planck came up with a term called quanta that he used to describe how particles absorbed or released energy. He came up with an equation that said that energy was equal to a constant times the frequency. What this meant was that particles only absorbed or released energy in certain amounts, not in a broad continuum. The constant in his equation is now called Planck's constant, and it has this value. It's kind of a weird number. First of all, it's really small, 10 to the minus 34, and the units are in joules times seconds. Typically, we see 2 units like joules per second, but this is not the case. It's joules times seconds. Another physicist that worked on this kind of thing is maybe recognizable from his picture. Einstein was German. He lived in Switzerland and Austria, and he was asked to be the first president of Israel when it was created in 1947. Einstein took Planck's equation and Planck's work and applied it to light also. Einstein proposed that light traveled in packets or small single wave pulses that he called photons. A single photon has very little energy. In the visible spectrum, it's only about 10 to the minus 19th joules per one photon. It's teeny tiny in terms of energy. Einstein took Planck's equation and said it was true not just for particles, but also for photons, where this is the energy per one photon in terms of Planck's constant. Einstein got a Nobel Prize for this work, as well as working on the photoelectric effect. In order to visualize quantization, how energy is only released or absorbed in certain amounts, we can talk about a couple of familiar things. One is potential energy. Potential energy can be calculated as the gravitational force on an object times its height above the surface of the planet times the mass of the object. So the higher something is, or the heavier it is, the more potential energy it has. It helps to visualize quantization as comparing it to heights available on a ramp versus a set of stairs. On a ramp, there's a continuous change in height that's available for an object, and an infinite number of potential energy positions. So an object could be here on the ramp, and it would have this height above the ground, and a certain potential energy. The object could be in a different spot, or the object could be anywhere in between those two places. There's an infinite number of heights available, and therefore an infinite number of potential energy positions. Compare that to stairs, which represents a quantized change in height. On a set of stairs, an object can only be on one part of the stairs or another, and so therefore it only has a finite number of potential energy positions. This is a lot like how energy of photons and particles works, in that they only have certain amounts of energy they can absorb or release in terms of their heights on a staircase. Here are a couple of problems to work that relate to energy and light waves. Don't forget that the equation we'll be using is the energy per one photon is equal to h nu. Pause the video, work out the problems. I'll have the answers for you. The first problem is pretty straightforward. All we have to do is use the energy per photon equation, E equals h nu. Add in Planck's constant and the frequency, and we can calculate the energy. I urge you to keep track of units as you're solving the problems in this particular chapter, because the units will really help you figure out what the units for the answer should be. So Planck's constant has joules times seconds. Frequency is seconds to the minus 1, or 1 over seconds. And so the units of seconds reduce to 1 and cancel out, leaving the answer as 5.27 times 10 to the minus 19 joules for every one photon. I always be sure to include the joule per one photon part to remind myself that that's the energy for every one photon. The second problem is a little more challenging because we don't know the frequency, but we do know the wavelength. We know from before that E equals h nu, and that frequency is equal to c over lambda. So this can transform to E equals h times c over lambda. Adding in Planck's constant, the speed of light in meters per second, and the wavelength in meters, the units of seconds reduce to 1 and cancel out, and the units of meters reduce to 1 and cancel out, leaving the answer in joules per photon. On the next slide, there's a couple more problems. It's important to recall that this is the energy calculation for every one photon. In chemical reactions that require bonds breaking, because the substance absorbs energy through a photon, and therefore that absorbed energy can be used to break a bond, that there's one photon that gets absorbed for every one bond that breaks. Go ahead and try to solve these problems, and the answers will be up shortly. From previous work, we know that a frequency of 7.95 times 10 to the 14 seconds to the minus 1 has a certain amount of energy, and that's energy per one photon. We can take the number of photons and multiply it by the number of joules per one photon to calculate the total energy available. The energy per photon comes from the previous slide. Converting it to kilojoules gives us 791 kilojoules of energy total, and that's in lots of photons, 1.5 times 10 to the 24th of them, over a mole. In the next problem, make sure you account for the per mole term in terms of the energy of the photons. We can start by calculating the energy per photon in terms of joules for every one photon. Then we can use that in the E equals h nu equation. Starting with the number of kilojoules per mole of photons, Avogadro's number can be used so that moles reduces to 1 and cancel out. This will tell us the amount of energy per one photon, and then convert from kilojoules to joules to give an answer of 4.9 times 10 to the minus 19 joules for every one photon. In order to calculate the frequency, the number of joules per one photon can be divided by the value of Planck's constant. The units of joules reduce to 1 and cancel out, leaving units of 1 over seconds, or seconds to the minus 1. So therefore the frequency can be calculated, and then it's just a matter of calculating wavelength in nanometers from there. And that result is 4.06 times 10 to the minus 7 meters, or 406 nanometers. That's the end of part 2 for the Chapter 7 lecture video series.